Let's talk about hydrohalogenation. Sorry, halogenation. This is where we're gonna add halogen to our alkene, right? Now, the same thing will happen in the sense that the reaction is an addition reaction, like we've been doing for all alkenes. If you've been watching those videos, your carbon-carbon double bond will break, leaving you with a carbon-carbon single bond, and then you add the bromine across the carbon-carbon double bond, right? So let's put these three hydrogens back. Let me number these carbons. One, two, three. One, two, three. So on carbon two, right? We have our hydrogen, put it back. Carbon number one, we have two hydrogens. Let's put them back. Here is what's different with when we add our Br2. I'm gonna make Br2 red. This reaction is what we call a reaction that is stereoselective, right? And of course, it's in the word stereo from stereoisomer selective. This reaction is considered to be stereoselective because one stereoisomer is formed in preference to the others. So remember what your stereoisomers are, right? So your cis and trans isomers are example of stereoisomers, your enantiomers, etc., right? So this reaction is what we call anti-stereoselective, right? Anti is similar to trans, which is what I'm showing here, your BRs will add on opposite side of the carbon-carbon double bond. So here's our carbon of the double bond, right? Remember the double bond break, leaving you with a single bond. So carbon 1, carbon 2, we add our Br to these carbons. Notice I add one at the bottom, one at the top. That's trans, right? Opposite sides. So this reaction is anti-stereoselective, which means your BRs or whichever halogen you have will add trans, which means opposite sides of the carbon-carbon double bond. We say the reaction is anti-stereoselective because, hey, guess what? It could have been where the BRs could have added on the same side. But the reaction is selective. It selects or it prefers or it chooses the trans product. So what happened is somebody did this reaction and realized that the BRs, they add trans. So that's why we say this reaction is anti-stereoselective. The trans product is formed over the cis product, right? We'll meet reactions where they add on the same side. When that happens, that reaction is a syn stereoselective reaction, okay? So when you make your flashcards when you're studying, you need to remember that your BRs add on opposite sides. Let's look at another example. I need to introduce it to something else. So let's look at adding, let us add, and whatever I do for Br2 or Cl2, it's the same concept, right? So let's do Cl2 in this case. And this reaction can be done neat, where you don't need a solvent, but in some cases they will add CH2Cl2. It's not gonna participate in the reaction, it's inert. It's just there to dissolve your starting materials, okay? So let's look at what we have here. We're adding Cl2 to this alkene. You shouldn't be freaking out right now because remember your focus, even though I changed the structure, it's right at, your focus is still at the carbon-carbon double bond. So your focus is here. Remember the carbon-carbon double bond breaks, right? Leaving you with a carbon-carbon single bond. So what you have is your ring without the double bond. That's the first thing you draw, right? The ring without the double bond. Then, okay, remember our CLs will add to opposite sides. So I need to show one Cl above the ring and one below the ring. Remember, to show above the ring, you draw your solid wedge. To show below, it's the dashed lines, right? Remember, each carbon, and notice my focus is only on carbon 1 and 2, every other carbon stays the same. Remember from our chair conformations, right? Each carbon, and of course the hydrogens are not shown. This carbon has a hydrogen that I have not shown, but remember, your ring, if one bond is up, the other bond must be down. So the hydrogen that is on carbon 1 is down. The hydrogen on carbon 2 is above, right? So here is carbon 2, your Cl is below the ring, so the hydrogen must be above. Remember from your chair conformation, on each carbon in that chair, and remember the chair represent the ring, one is above, one is below, okay? I need to show you something and you need to remember this. When you have your reactions with your alkene, right, and you start with a chiral molecule, this cyclohexene is a chiral because there's no chiral center in here. Cl2 clearly don't have a chiral center, right? So when you start with achiral molecules as your starting material, don't forget this, and you generate a product that has one or more chiral center, so if it has one or more chiral center, right, you generate a racemic mixture. You should have learned racemic mixture already. If you have forgotten, it's 50% of each enantiomer, right? 50% of each enantiomer. So let's identify our chiral centers in this molecule. There's a chiral center here, and there's a chiral center here, right? Remember, a chiral center is that atom that has four single bonds that are different. This is different, this is different, that's different, this is different. So we have two chiral centers, same thing here. What's bonded here is a Cl, a hydrogen, then this group, then that group. Four different groups on carbon 1 and on carbon 2. So I have two chiral centers here. Remember how you draw your enantiomers, right? So, and if you don't remember, go back to my videos on stereoisomers. So, this is how you get your other enantiomer. So this is one enantiomer. To get the second enantiomer, which is formed in a racemic mixture. So remember, once I start with achiral starting materials and I generate one or more chiral center, I automatically will have a racemic mixture. So this is one enantiomer. To get the second enantiomer, because my racemic mixture is two enantiomers in 50-50%, all you do is swap the groups at each chiral center. You have to swap the groups at all the chiral centers for it to be an enantiomer. I hope you remember that. So let's draw our second enantiomer. So remember, I'm swapping the groups here at carbon number 1. So this is carbon 1, this is carbon 2. Let's swap our groups. So, of course, you have one group below. The group below this time is the Cl, and our hydrogen is going to be what's wedged. All I'm doing is swapping the groups. Carbon number 2, my group that is above this time around is the Cl. The group that is below is the hydrogen. So these are my two enantiomer, A, B, and they're formed 50-50, which is what a racemic mixture is. So remember, if you start with a chiral starting materials and you end up with one or more chiral center, you produce a racemic mixture. Notice um, for this, we did not have to worry about forming. Actually, for this one, we only have one chiral center, which is right here. So let's go back to this. I didn't show you a chiral center in this one, which is fine. So carbon number 1 is not a chiral center because you have two groups bonded that are the same, right? Carbon 2, you have a hydrogen, you have a CH, you have bromine, and then all of these groups. At carbon 2, we have a chiral center, right? To show your racemic mixture, all you have to do is use solid wedge, your solid wedge and your dash lines, right? Make the Br and the hydrogen one solid wedge, one dash, and then for the enantiomer, swap them around. You should try that for yourself and see. It's the same thing you're doing. Like here, all you're doing is this is the chiral center. So swap. So the two groups, like your bromine and your hydrogen, give them wedge and dash on one, and then to get the second enantiomer, you do what I told you. You swap the groups. So you end up with you're gonna get two molecules, right? So go ahead and try this one for yourself based on what we did down here. If you have any questions, drop them in the comments. But yeah, it's the same idea. Just remember that once you have something achiral, right? Achiral and you generate a chiral center, you will get a racemic mixture. So this one is a racemic mixture. And this time around, you only have one chiral center.